Now that we have some idea of how the kernel heap works, let's take a look at some of the kernel heap protection mechanisms that can be compiled into the kernel to make it more difficult for an attacker to exploit it. Now, the first mitigation that is worth mentioning is something that's called Freelist randomization. By default, when a fresh slab is created, the Freelist will default to being in order. And what I mean when I say in order is for a fresh slab, the first slot that will be used to satisfy an allocation will be the first slot on the slab. Then with a, for instance, kmalloc or kmem cache alloc were called a second time that drew from this slab, the second allocation would come from the second slot. The third allocation would come from the third slot. This would be in order. The kind of default free list is in order for a brand new slab. Now, this is beneficial to an attacker because an attacker can easily know where in memory allocated objects relate to each other. And generally speaking, an attacker's goal is to get two objects right next to each other in memory, or to strategically place objects in memory such that there is some property. But the kind of key for the attacker is to know where these objects are being allocated in memory to then take advantage of the relationship between those locations. And so by having this in order, it's easy for an attacker to know the relationship between allocations on a fresh slab. So Freelist randomization does exactly kind of what the name implies. The Freelist randomization configuration option randomizes the free list. So what is the impact here? For a fresh slab, you have no guarantees about which slot will be returned for those initial allocations that are drawing from the slab. So the first allocation may draw from slot 0, but then the second allocation may draw from slot 14, which is what we see here. The third allocation against this slab, maybe that draws from slot 16, right? The order of the initial allocations against a fresh slab is randomized. Now, the way that this randomization is done is for the cache initially, a random sequence of indexes is generated. These indexes are integers, and they are stored in the kmem cache random sequence location. So it's stored as a member of the kmem cache as a linked list. And so there's this linked list that represents the order of the default free list order. But recall that the free list is essentially a singly linked list, and freed objects of a singly linked list are pushed to the head of the list. Now, the order may be randomized once at slab creation, right, when the slab is first brought in, but if an attacker has the ability to allocate many objects, then the attacker can allocate the entire slab, let's say. And then the attacker could free them in whatever order the attacker desires. And that means that the attacker can determine the order of the free list, or the attacker can set the order of the free list based upon the order that the attacker frees the objects that were allocated previously. Now, this still presents a challenge to the attacker, because the attacker may be able to allocate all of these objects, but the attacker doesn't know by default how these objects relate to each other. And so this creates an additional challenge for the attacker, because the attacker must use some other type of vulnerability to figure out how these kernel objects relate to each other. Because in a typical exploitation scenario here, the attacker isn't in the kernel. So the attacker isn't the one that is getting these raw pointers, right? The attacker isn't the one that is obtaining these kernel objects. Instead, the attacker is encouraging the kernel to allocate these kernel objects. The attacker is typically somewhere in user land. and they are using, for instance, syscalls, or they're calling ioctl on a kernel device, and that is triggering the allocations inside of the kernel. And so the attacker doesn't get to see the raw memory addresses of the object. The attacker just knows that they did create an object based upon what they have triggered inside of the kernel to occur. So how does an attacker figure out how these allocations relate to each other? Well, the attacker can rely on a strategy that we've seen in earlier heap content. An attacker can rely on, for instance, a use after free bug. If the attacker has a pointer into a freed slot, and that slot is not the last slot of the free list, then that slot is going to contain a next pointer. So in a use after free scenario, the attacker can build a primitive as shown here, where the attacker has a pointer to, for instance, slot 0, which slot 0 contains a next pointer that identifies the address of slot 1. The attacker could then malloc twice, and then, for instance, free slot 2, then free slot 0. Then use this same primitive to read the address of slot 2, at which point now the attacker knows the relationship between those two allocations because they can compare the distance between the two pointers that were read. So a use after free scenario would be great for an attacker, but the kernel has another mitigation strategy that makes this scenario more difficult. And that is something that's called Freelist hardening. When I described the scenario here above with the use after free and kind of leaking next pointers, hopefully this reminded you a little bit about how Tcache's linked list works. Because it is still a singly linked list that relies on next pointers. And how did Tcache protect next pointers? Tcache used something that was called safe linking, where they XORed specific values with the pointer to obscure it. So that way, if the next pointer happened to be visible or leaked to an attacker, the initial value that's leaked doesn't provide any useful information. Well, Freelist hardening works very similar to safe linking on the Tcache side. The logic is we're going to XOR some values with the pointer, and this should obscure it to make it functionally useless to the attacker. Now, safe linking had kind of an interesting mechanism as far as how the XORing was done. It was the pointer with the address of the pointer bit shifted, and we definitely took a look at that in the Tcache module. The Freelist hardening works slightly differently as far as what is exactly occurring to obscure the pointer. Instead of doing some bit shifting, there are three values that are being XORed. There's the pointer itself, there's the address of the pointer, and then there is a random cache specific value, which is just referred to as random. And we see here in the code snippet that random is attached to the KMEM cache. So there's this random value that is a member of the KMEM cache, and that random value is XORed with the pointer as well as the address of the pointer. And so that this would obscure it. So now the attacker can't work just off of this primitive. Or can they? Well, let's think a little bit about what's going on here. So here's our scenario, and the attacker has that same use after free primitive. Well, what can the attacker leak? Well, in this scenario, the attacker can leak the encoded value, which is what we saw right here. The encoded value is the pointer XORed with the pointer's address, XORed with the random value. And so in this scenario, which is where we were earlier, the attacker can read address of pointer, XORed with pointer, XORed with random. Not particularly useful. But what an attacker can recognize is they can, if they have a use after free and they have the ability to influence the kind of state of the free list, they can create this scenario. What happens if the use after frees next pointer is null. It's very similar to what we had initially. If we were to create the scenario where there is no pointer value, then the attacker can read the address of the pointer XORed with the random value. Now, neither of these are useful really on their own. Well, that's not entirely true. But they don't help the attacker know the location of any of the slots on their own. But together, these two values allow the attacker to reveal that pointer. So the first thing that they can obtain is this obscured pointer from this scenario here. The second thing that the attacker can obtain is, well, what if we made the pointer null, right? We set it up such that the useAfterFree is the last item in the free list, in which case its next pointer is null. Well, then the attacker can obtain that address of the pointer XORed with the random value. If the attacker can obtain both of these, then the attacker can XOR them together, at which point the attacker has revealed the pointer. And so that is sufficient not only to decode an obscured value, right, which is what we've just shown right here, but this second value right here, the address of pointer XORed with null, XORed with random, is sufficient to encode a pointer. And so this is everything an attacker needs to influence the free list to either reveal the location of slots that are on the free list or overwrite pointers on the free list to redirect what values will be returned from requesting an allocation from this cache. Another scenario that an attacker may take advantage of is an out-of-bounds access scenario. So let's take a look at what we have set up here. Well, what if the slab is configured such that there is a valid object that is allocated, and there's a valid pointer to this object because it was allocated? Now, immediately after the valid object, there happens to be a free slot, and this free slot happens to contain a next pointer. Now, this next pointer could be encoded, at which point the attacker has to involve the steps that were described earlier. But right now, let's imagine that it's not encoded. Well, the way that data is typically transferred from userland to the kernel or from kernel to userland is via the functions copy to user or copy from user. And so what if this object is supposed to be, in normal functionality, copied to userland or copied from userland to the kernel? Well, if the attacker, instead of manipulating the pointers that are involved, somehow gains control of the number of bytes to copy, then the attacker can access or influence bytes that are outside of the kernel object that was allocated. So in the event the attacker can copy to the user more than the intended number of bytes, what would happen? Well, the attacker would be able to copy this entire object, and then let's say that they somehow managed to double it. Well, they would leak this entire object plus all of the bytes of the object that is next in memory here, that follows it in memory. In this case, we would be leaking the object that is located in slot 1, as well as all of the bytes of the freed slot 2. And in this case, that contains a next pointer. And so now the attacker has gained some information about the addresses that are being used in this slab. Now, what if the attacker can do the reverse? And the attacker can copy from userland to the kernel, right? So this would be a scenario where, like, the kernel object is intended to contain some userland data. And again, let's pretend that the attacker somehow manages to double the size of that copy. Well, then the attacker can write this entire object plus all of the bytes of the freed slot after. And if that is the case, then the attacker can overwrite this next pointer which would then influence what pointers would be returned from future allocations against this slab. And so this is a general out-of-bounds access scenario. We described both an out-of-bounds read as well as an out-of-bounds write. Well, for those objects that are intended to be used for copying data between userland and the kernel, there's an additional mitigation that can be configured called hardened user copy. Right? So these mistaken copying back and forth from the kernel can result in these out-of-bound accesses or information being leaked that wasn't intended. What this mitigation enables is the cache now has an additional two members. It has an offset member and it has a size value. And these two values represent the region of memory that is allowed to be copied and transferred back and forth from userland to the kernel. And so these values can be used to verify that the bytes that are being transferred to and from the kernel are within the intended range. We can take a look at kind of what that looks like. So up above here, we had this kernel object, right? And we said, well, they could copy this entire kernel object. Well, what if instead of starting the copy at the beginning, right, the intended use of this kernel object was to just copy a small subsection of the entire kernel object? Well, we can define that with these offset and size values, where if this is the start of the object, we can't copy anything between the start of the object and the start of the object plus offset. And we can't copy anything past the size added to the offset added to the start of the object. So we are only allowed to copy this region shown right here. If somehow the attacker was able to manipulate these values so that copy to user or copy from user was accessing memory outside of this specifically defined range of the kernel object, then it would fail. The reason that this can work is because a cache, as you'll recall, is created with a specific size slot in mind. So what we're doing here is we're creating a cache not only with a specific size slot in mind, but we're creating a cache with a specific object in mind. And the offset and size values are stored inside the kmem cache struct. And so that means that all kernel objects that are allocated against the cache will have this hardened user copy check occur. So what does an attacker do if this is properly implemented and the kernel objects that the attacker is interested in have hardened user copy and they're being allocated against a cache that is properly employing this? Well, what an attacker would question is, well, where exactly are these values being checked? Well, one of the things that I mentioned when I kind of initially described this scenario was, well, copy to user and copy from user are kind of the de facto ways that data is transferred from userland to the kernel and from kernel to userland. And that is, broadly speaking, true. Inside copy from user and copy to user, they call kmem cache create user copy. And so a separate copy is created. And during that process, check heap object is called. You can definitely check out the Linux source if you want to follow the call stack here. But this check heap object is where these values are actually compared and verified. And so if copy from user is utilized, the check will happen. If copy from user is used, the check will happen. But not all operations that copy memory verify these values. For example, what happens if instead of using kind of the approved standard of copy from user and copy to user, there is functionality in the kernel that uses memcopy. Memcopy has no idea that it's supposed to go and look at a slab allocator's cache and then find this offset in size and do some type of verification step. Memcopy just, here's where I start, here's how far I go, copy, go, brrr, right? And so an attacker would be very interested in finding locations in the kernel that copy from user land to the kernel or from kernel to user land via other methods than these two. And these certainly do exist. The last mitigation that I'm going to talk about is something that we should already be familiar with, and that's KASLR, which stands for Kernel Address Space Layout Randomization. Now, KASLR works very similar to userland ASLR in the sense that what does ASLR do? ASLR randomizes some bytes in memory addresses, which makes it more difficult for an attacker to know where things are located in memory. Now, in userland ASLR, these addresses are randomized every time we execute a new process. But we don't have that same opportunity to re-randomize with kernel memory, because the kernel memory gets kind of stood up when the system first starts up. We can't re-randomize in the middle of running. And so KASLR randomizes these addresses per boot. The addresses are randomized or obtain their randomized bytes when the system first starts up, and it's going to be a constant from the time that the system has booted until the system shuts down, and then it would be re-randomized next time the system starts up. Now, the attacker's general strategy for combating KASLR is the exact same thing as combating ASLR. The strategy is get a leak where you know what it is, compute an offset to a base address, and then based on that base address, you can suddenly know where things are located in memory. So how do you get a leak from the kernel? Well, one way that you can get a leak is by taking advantage of something that is known as a kernel oops. So the kernel certainly can encounter errors, right? There could be a bad kernel module, and we don't want the kernel to drastically fail every time a small bug occurs. So if the kernel encounters an error that it recognizes is non-fatal, it will attempt to recover from it. If the kernel is configured such that oops messages will be output, the error details, including the register information, will be printed out and accessible via dmessage. So on the Dojo VMs, you could run dmessage, and then from outside the VM, which is what I'd encourage, you can see that same information by using the VM logs command. And so by triggering an error inside of the kernel that's non-fatal, that the kernel identifies as something it can recover from, it can leak register information, including kernel addresses, if a kernel address happens to be stored in a register at the time of the error. Now, the kernel can also be configured to panic on oops. Now, what's a kernel panic? Well, a kernel oops was if the error was non-fatal. It was, for instance, some type of memory access, and the kernel just identified we're trying to access an invalid memory address. We don't need to fail the entire kernel. We just need to report this error, and we can carry on, right? We can recover from this error. That is what triggers an oops. But if an error is so catastrophic that the kernel is incapable of recovering from it, then the kernel will do something that's called a kernel panic. A kernel panic is very similar to an oops in the sense that an error message can be output, but then the system essentially locks up and execution cannot continue. The kernel identifies that it has entered a non-recoverable state, and it ceases to operate. And this is what's known as a kernel panic. Now, the kernel can be configured so that these non-fatal errors that typically output an oops will instead result in a kernel panic. In that type of a scenario, it's a lot harder to get the kernel to leak kernel addresses because we no longer have this kind of oops mechanism to trigger that. One thing to keep in mind is that the kernel responds to all processes. And some of the panic checks occur within the context of a specific process. So like if I had a process that is deliberately injecting bad addresses into the kernel and then causing the kernel to dereference them, that is something that the kernel could identify. This process intends to utilize these bad addresses, and this process intends on accessing these bad addresses, right? The kernel can identify, look back at previous execution and kind of identify the intent and say, this is clearly what was meant to happen, and this is unrecoverable. But some of these panic checks may be avoided if instead of doing all of that in one process, the triggering access occurs in a separate process than the process that's setting up. I'm purposely being a little bit vague here, but by leveraging multiple processes, you can get the kernel to not perform some of the checks that would result in a panic. And so that's something that is definitely worth considering if you are trying to get a leak to defeat KASLR on a system that is configured to panic on oops. So once you've obtained a kernel leak, the next thing that you want to be able to do is to determine whether or not the address that you've leaked is useful for identifying the kernel base address, right? Can I use this address to defeat KASLR? And there's a couple ways that you could probably do this, but the way that I'm going to show is to utilize GDB and the pt.dump plugin to reason about the value that you've obtained. So my terminal on the left-hand side is inside the VM. My terminal on the right-hand side is outside of the VM. Now, I'm not going to trigger a kernel oops for this demonstration. I'm going to leave the oopsing as an exercise for the learner. But we will instead cat proc kalsims, and we will grep for init cred. And we'll pretend that this is our leak. It is necessary to be root when you can't kalsims, or else you will get the zeros, as you see right here. So we'll pretend that this address right here, I've somehow managed to obtain via a kernel oops or some other type of leak. Now, once I've done that, outside of the VM, I'm going to run sudo vm debug. Now, generally speaking, you don't need to run GDB as root. However, for this specific plugin to work correctly, you will want to be root. We'll take a moment for GDB to load the symbols from the kernel. And now we have a debugger attached to the kernel instance that's running on the left. Now we can show that KASLR is enabled here because if we ask GDB, where is init cred located, it's actually going to give me the wrong address, right? We see 82A, and over here we see A8E. And so these bytes are randomized. And so that is a bit of a problem. But we can rely on proc kalsims to get the address of symbols that we're interested in. So, while debugging, that is. So if I want to use this ptdump command, it is located on the dojo. It's located in /opt ptdump, and the file that you are interested in sourcing is pt.py. So it's already there on the dojo. Don't worry about trying to pull it in from GitHub. To utilize the plugin at the GDB prompt, we can source that exact path, opt ptdump pt.py. And we now have access to the pt command. You'll notice that this outputs a bunch of regions of memory. This output is very similar to the VM map command from Jeff. The difference is VM map is going to show me user land addresses, where ptdump is going to show me all addresses, including user space, which we see right here. And so here's the user space addresses that are in use. Another region that is notable here is FizzMap, which we may have interacted with in an earlier module here on pwn.college. There are some fun things to do with FizzMap. And if we get all the way back to the tail end of this output, we do see where the kernel is loaded in memory. So how do I know where my leak is? Well, if we copy our leak, we can use the pt command and pass it has, and then the address that we're interested in. And ptdump will show us the region of memory that this address, or this pointer, corresponds to. So this address is located in this region of the kernel's memory. Now, the next thing that we would probably want to verify is, well, are these regions of memory contiguous, right? Are there gaps here? And we can determine that by doing some pretty simple math here. If we start off with the kernel base address, and then we add the size of this first region, we could then add the size of the second region, and then we could add the size of the third region. I think you see where this is going. We're then going to include the size of the fourth region. Now, as long as the result of this addition equals the starting address of the fifth region here, then we know this is all contiguous memory. And what we see here is the result of the addition is 98D000, and that is the base address of this last section of the kernel. Now, if we were to go one section further, we see A9C and then 5 zeros. Well, what comes after the kernel? Well, it's actually this kernel module. And so kernel modules are not contiguous with the kernel, but all addresses from the kernel are contiguous with the kernel. And so what that means is when I run this pt has command, as long as this section lists kernel, then we know that we're in one of these 5 sections, and the address should have a constant value or a constant offset to the base address of the kernel. And we can compute that constant offset by doing some simple subtraction. We'll take the leak that we've managed to obtain, and then we will subtract the base address of the kernel. See if I can, I have it right down here. And that now gives me a magic constant. We're just going to hang on to the magic constant for a moment. We want to prove that we can use this offset to compute the base address of the kernel. So let's get out of GDB. Let's VM restart. The reason I'm doing VM restart is because KASLR randomizes on boot. So now what I'm doing is I'm rebooting the VM. And this is the same type of re-randomization that would occur if you started off in practice mode and then you wanted to apply your exploit in challenge mode. We'll do the same thing here, where my terminal on the upper left here is going to connect to the VM. And we will sudo cat proc KASLR, and we'll grep again for a init cred. What we should see, this has bytes BDA. We were to scroll up a little bit here, we see that it did change, right? It has randomized. Now my claim is, by using my leaked pointer and our magic constant, we can predict what the kernel base address will be. But we do need to be able to verify that. So let's go ahead and sudo vm debug, and we'll just do our math inside of GDB. So if I take my leak that I've somehow managed to obtain, and then I subtract the magic constant that I've computed, this is where I think the kernel base address is. Let's bring in ptdump. And let's see if we can be a little bit cheeky and say, what section contains this address? And what we see is the address that I predicted to be the base address of the kernel is in fact located in the executable section, which we saw was the beginning of where the kernel was loaded into memory. So I was able to compute the base address of the kernel. Now, once I have the base address of the kernel, locating other objects or interesting locations in memory is as easy as computing the magic offset from the base address of the kernel to the point of interest that I am interested in. And that would apply to locating ROP gadgets, that would apply to locating interesting regions in the data segment. Anything in the kernel can be computed by finding some magic constant to the base address of where the kernel is loaded into memory. So hopefully that gives you some idea of what to do once you've managed to obtain a leak of kernel addresses.